Hello, welcome to today's webinar. This webinar has been motivated by the number of questions that I've gotten over the last 25 years from researchers and graduate students, and the various situations and difficulties they have in either planning or analyzing their designed experiments. So I've put together a set of guidelines for doing just that, planning and executing DOEs. Everybody is on mute at this point. If you do have any questions, you may type them into the questions pane and I will address them at the end of the presentation. If there are questions that I am not able to get to, I will definitely answer them via email later on today. And just a note that this presentation will be posted to our statties.com/webinars page as soon as the recording is available. I'm going to be referring frequently to additional presentations that you can view on all the different topics that I'm going to be bringing up. And these have been posted on our YouTube channel page, which is Statistics Made Easy by StatEase. And on that channel, look for the academic corner. In here, I've put resources for researchers and students, and here's a selection of them, and you can scroll to the right and you will find even more options. The four topics that I plan to cover today are planning your experiment, then actually running and executing the experiment, analyzing the data, and confirming the results and what you do to wrap up your study. So let's start with planning your experiment. Now, the most important part of the experiment is the data that you're going to be collecting. So defining the response that will be measured and making sure that that the measurement system is going to produce accurate and ideally numerical results. We try to avoid pass-fail if at all possible, as it's very difficult to fit a polynomial to pass-fail data. So people don't really think about the fact that, you know, the entire success of the experiment is not necessarily on the design that they choose, but it's actually on how well they collect the data. So you need to invest time and energy into that measurement system and start there. I've actually seen companies devote months and years to making sure that their measurement systems are accurate and well defined so that their future data collection will be as informative as possible. So start with the response that you're going to be measuring. Then think about the factors that are likely to influence the response. And also think about the range that you want to vary those factors over. Just a reminder, you have to choose a factor range, you know, your low level to high level, that is far enough apart that you expect that will trigger a change in the response. If you don't trigger a change in the response, then there's going to be nothing to analyze. You have to set those factors wide enough apart that you're actually going to see a difference. That the goal of design of experiments is to trigger a change and then understand the cause and effect relationship between the factors that you changed and those responses that you're measuring. Then you choose a design that will provide the information that you need, and you want to consider the strategy of experimentation at this stage. Are you doing a screening design or a characterization design or an optimization design. And I'm going to define those on the next few slides. So I will get back to what I mean by choosing a design. But the fourth point is to plan in advance that after you conclude the designed experiment, you're going to go back to the system and run model verification points to confirm the analysis and interpretation results. You know, this is really key to research and is one of the things that is so often overlooked. People run their experiment, analyze the results, and think that that's the end. And then I ask, well, did you prove that these results worked? And you know, they look at me blankly and don't know what I'm talking about. Well, you have to confirm the results. If you don't prove that the prediction model out of the experiment works, then you haven't finished the job. You haven't finished your research. So let's go back and talk about choosing the design. This is known as a strategy of experimentation, and it is fully spelled out in one of our YouTube webinars videos called Know the Score for Multi-Factor Strategy of Experimentation. So that is found on our YouTube channel. Basically, we break it down like this. There are 3 stages of experimentation. There's the screening stage, where you maybe have a few factors that you absolutely know have effects. And then you have a bunch of factors that you do not know if they have effects or not. Those are the ones that you really want to focus on in a screening study, a screening DOE. And I'll get to more details on what a screening DOE looks like. But from a concept standpoint, we are just trying to detect the main effects in this type of design. And you know, the output of this design would be a conclusion that says something like pressure has more of an effect than temperature, which has more of an effect than time. You know, you may rank the main effects of the factors that you're studying in this type of screening design. Once you have identified the likely important factors in the system, then it's probably time to move on to a broader experiment that would be a characterization type of design, where you're really trying to fully understand both main effects and the interactions that are in your system, and test for curvature. Through screening and characterization designs, they're usually done with 2-level factorials, and there's an underlying assumption that all the primary effects are linear effects. But at some point, you want to test to see if that's a valid assumption or not. And so throwing in some replicated center points to test for curvature, test for nonlinearity, is a good point. So often we'll do that when we reach this characterization stage. Then many experiments are run by just jumping into full optimization designs using response surface methods. This might be using central composite designs or box-Benkin designs or optimal designs. And the goal here, the objective of these designs, is to make precise predictions. Now, hopefully, you've already narrowed down the field of factors so that you're only doing a design with the key critical factors. And at this point, you're able to model both linear and nonlinear polynomials. Then the fourth stage is, as I mentioned, verification, where no matter what design you do, either characterization or optimization, if you're using a 2-level factorial or you're using a response surface design, you need to step back, figure out the best set of conditions, and do some confirmation runs. We will talk more about that at the end of today's session. But if those verification runs confirm, then you get to celebrate. And if they don't, then you need to back up and consider from a engineering or science point of view, if you missed some variables, if you didn't set your ranges far enough apart, or if there simply are no relationships between the factors and the responses. So in any case, you need to back up and kind of think about what might have gone wrong. So choosing the design. For one, use DOE software. There are many, many options in the software, and but here's the basic categories. I've mentioned the screening designs. Now, the fundamental thing behind screening is that we have to assume the interactions exist in the system. You know, although a screen design is not meant to identify the interactions, you have to assume that they are present in the system. So you need a quality design that keeps your main effects information unbiased from those two-factor interactions. So for this purpose, resolution 4, yellow designs, or resolution 5, green designs, or even better, are what you're looking for. You don't want to use resolution 3, red designs, which include Plackett Berman and Taguchi, some Taguchi designs. So I am just going to pull, well, I'll look at these and then I'll pull up the software in just a minute. Characterization designs use designs that can estimate all two-factor interactions. So full factorial or resolution 5 plus designs. And as I mentioned, you might want to add center points to test for that non-linearity. And then optimization. Use a response surface design, such as central composite, Fox-Bankman, or optimal designs. One last note. If you are studying formulations, if your work is with a formulation, then you want to go directly to mixture designs, which have options for either screening or characterization and optimization, which are likely done using an optimal design. So let me just open up the software. I've got StatEase 360 here, which is our latest, most advanced DOE package. It is based on Design Expert software, but has some new additional things. And there is, at the very front of this, either Design Expert or StatEase 360, there is a design wizard. If you click on that, it asks you, what is the purpose of your designed experiment? And as you click on the options, there's text here that defines, the type of design objectives that you have and gives you some advice and suggestions. And so it leads you through a series of questions. And again, if you don't know what they are, just click on the options and it will define them, maybe give you some examples, until ultimately it will finally ask you, how many factors do you have? How many runs can you do? And based on that information, it will provide some options. So for instance, 4 factors, 21 run budget, and it says, hey, you could do a 2-level factorial with 5 center points. And if I chose that, it would take me directly to that design for factors and 5 center points added in. So that design wizard is really handy for identifying, you know, a good design to start with. And, you know, just in general, we have all the factorial designs. I was talking about the red, yellow, green designs. This is like a stoplight effect with green, and the full factorial is giving you the most information. And yellow designs, good for screening. I would stay away from the red designs if you're trying to identify factor effects. And then over on the side here, there's some other options: minimum run characterized designs and minimum run screening designs, all good options. If you have multi-level designs, then you might want to go into an optimal factorial design or a response surface type of design if they are numeric factors. Okay, so we will get back to more of this later, but you know, I really want to emphasize using DOE software to design your experiment, not just bringing it up afterwards. So many people design their experiment by hand, perhaps looking at somebody else's thesis or research paper that they did prior. And then they come later and say, well, now how do I get this into the software? That's the wrong approach. And I'll say most graduate student DOE analysis problems are caused by errors made in building the designs. So analysis problems are caused by errors in building the designs. If you use DOE software to design your experiment, it will give you better, more modern design options. You know, you don't have to use what was used by somebody, you know, 20 years previously. There's probably better options out there today. And it will remind you to consider adding center points, doing blocking, doing replicates. We'll talk about all those. It also allows a check of the power or precision to size the design properly. We'll talk about that in the next slide. And the final design layout is provided in a nice random run order. And that is, it's very easy to add the response data, just copy and paste the whole design from Design Expert to Excel, and then you can paste the responses back in. I will just build, you know, just a simple design. I'm not even going to put any information into it, but I just want to show you that you can take your design layout, you can copy with headings, and you can paste it right into Excel. I'll do a Control V to paste it in. And then here you can, you know, type in your response values. Then when you get done, all you have to do is take that column and paste it right back into the software. So it's very easy to get information in and out of Design Expert or Studies 360. Okay, let's talk just a minute about checking the power or precision of the design. This is the concept of making sure that your design has enough runs that it can detect all of the information that you want. So if you are doing a factorial design, then you do sizing using the power calculation. And power is the ability to detect an individual effect or coefficient. And so it's, you know, important to check the power, make sure the power is above the guideline of 80%. Now, many more details on this are given in the video. How many runs do I need using power and precision to size DOE? So I'm only giving just a brief overview. Learning DOE cannot be done in an hour. DOE is a long education, and so we have, you know, many supporting videos to give you little bits of information as you need it. The sizing of the design is extremely important if you're running a design. I'd say anything less than 16 runs, you know, so if you're looking at running at an 8-run design or a 12-run design, then checking the power is really critical. It's also critical if your signal to noise ratio is less than 2. So even with the 16-run design, you better check power if your signal to noise ratio is less than 2. If you're doing a response surface or a mixture design, then you use something called precision. This focuses on the ability to predict the mean response or the average response with a certain amount of precision, a plus or minus delta. So going back to a factorial design, we have to define the minimum change in the response that you want the DOE to detect. So if your response is yield, are you trying to detect a 2% change in yield or a 3% change or a 5% change in yield? What's that minimum change in the yield that you're interested in? Then you also need to know the standard deviation of the response using some historical data. And we put those two pieces of information in, and then we look for a power of 80% or greater. If you're running a response surface or mixture design, then we use something called the fraction of design space graph, and we change, rather than just trying to detect an effect, now we're trying to get really good predictions. So we want to define the precision of the average prediction. So that precision would be, I want to predict my yield within plus or minus some amount. So maybe I want to predict my yield within plus or minus 2%. You know, so that would be the precision of the prediction. Again, we enter the standard deviation of the response, and we're looking to have the amount of the design space area that can give us predictions with that amount of precision. So we just verify that our design space is adequate, that basically we have enough runs to be able to answer that question. Okay, so that was just, you know, really brief concept overview on the power and precision, but again, I'm going to refer you back to this video for more. Okay, so spend more time planning your experiment and thinking it out. Whatever you're doing right now for, you know, the amount of time planning your experiment, double it. You know, just spend more time, because that is just so important, so key. Then a few tips on actually physically running the experiment. You know, of course, control things that could cause unexpected variation. That's number one. And I think most people, you know, understand that, but think about it. Think about the whole process of running the experiment Anything that you can manage and keep under control is to your benefit. There are sometimes variables that are going to vary, but you're not studying, such as if the experiment is going to go over 2 days or 3 days, then you might want to block on those days. If you have to use 2 or 3 different lots of raw material, then you might have to block on that. Or two pieces of equipment that are technically identical, but you know they're not identical. Again, this is thinking and planning ahead of time. So you plan the blocks during the design of the experiment so that they are statistically correct. This will be better than recognizing after you've run the experiment that you should have blocked and then trying to go back and add them in. Then it's not statistically blocked. It might still be a benefit, but it's not as good as if you had thought about that ahead of time. Think about how you're going to run your replicates. The analysis expects that replicates are run at separate points in time. So if you have 2 runs that are the identical combination, then you run one early in the experiment and you run one later in the experiment. The variation between those replicates should contain all the natural process variation. Don't group the replicates together. Don't copy the response measurements from one run to another. The consequence of not running your replicates at separate points in time is an invalid lack of fit test. And I'm going to get a blog up in the next week or so on the lack of fit test. That'll be on the homepage of our website, because we get lots of questions about lack of fit tests, but many causes of the lack of fit tests being significant are that there is very, very little variation between the replicates, an unnaturally small amount of error between the replicates, and that comes from not running those replicates at different points in time. You want to use the random order provided by the software as much as possible. But I'll say there's this exception. If you have looked through all of your results or all of your planned runs, if there is a condition that might not work, then run that combination first. Check it out. Change or edit the run number and make that the run number 1. If that run works, then great, continue on with the rest of the experiment. If it doesn't work, then you can replan the experiment and not lose any runs. But ideally, the run number or the random order is in there to protect you against lurking changes in the system that might otherwise bias any of your analysis results. Remember to document anything out of the ordinary that happens during your experiment. You might find those notes to be really important for diagnosing any unusual analysis results, such as if you have an outlier in your data, you can go back to your notes and say, did anything happen during the running of that particular combination, that might have resulted in getting a result that just doesn't fit with the other results. So documentation is really important. And of course, don't forget to include time and resources for running those follow-up and confirmation runs, as verifying your results is a key part of research. Let's turn to analyzing the data. I want to show you just a few things that I see people missing when they're analyzing the data. We have two procedures. We have the factorial analysis, and we have a response surface analysis. So I'm going to look at both of these. I'm actually going to pull up a file and just give you a brief review. We usually start with the effects button and use the half normal plot to select effects to include in the model, leaving the remainder to be pooled together in the residual. Then we go to the ANOVA, and then the diagnostics, and then the model graphs. There is, I'm just going to point this out right here, there is a webinar, a YouTube video called Graphical Selection of Factorial Effects that really goes into using the half normal plot and the Pareto chart. So I'll refer you to that, but let me just pull up this file. Okay, so this is a five-factor half fraction design. And so we start with the analysis. We have yield as the response, and we click Start Analysis, and you get the half normal plot and the Pareto chart. On the half normal plot, the goal here is to simply make a quick visual split of your terms. You want the ones that are not normally distributed to go into the model. And so I can actually just grab all of these. These terms are jumping off of our normal line. This line will fit all the terms that are normally distributed. Those belong in the residual. They are pooled together and put into the residual. The ones that are jumping off the line are likely significant. We'll find out whether they are or not once we get to ANOVA, but they are likely significant. So you want these together and these together. So you have two groups. That is all you are doing with this half normal plot. We have to use a tool like this. It is the best tool for analyzing two-level factorial designs because our eyes can see patterns very, very well. So you grab all the ones that are off the line, and then you click on ANOVA, and then you verify that the overall model is significant, and you verify that the terms are all significant. The one exception to significance would be if a term is not significant but is needed to maintain model hierarchy. Model hierarchy means that if you have an interaction like BD, both parent terms need to be included in the model. And we have that here. We have both B and D. In this case, they're all significant. But let's say that D was not significant on its own. It's still critically important that it be in the model to support the interaction term. And the same with DE. That has the two parents D and E also in the model. So your model should be statistically significant. That means p-value is less than 0.05. And another thing to look at, now with a two-level factorial, it may or may not be that important, but I always do look at the R-squareds, not the raw R-squared, that can be misleading, but the adjusted and the predicted R-squared to find out how much variation in the data is being explained by the model and how much variation in predictions is being explained by the model. So we have 98% and 97%. So these are very, very high. This is going to be an excellent prediction model. Sometimes, well, many times they're more realistically, they might be down at 0.6 or 0.7, you know, which is still okay. It's still making predictions. There's just more unexplained variation in the system. Okay. Then the other thing that you need to do is check your diagnostic plots, and some of our other webinars go into checking the diagnostic plots a lot more. I'm not going to spend much time on it. Just to say quickly, you need a straight line on your normal plot of residuals. You need the residuals versus predicted to be a really random scatter, as they are here, and you don't want any outliers. And outliers would be points outside the red lines. The residuals versus run chart can also show you any trends. There are none here. And then make sure you look at the Box-Cox plot for evidence that you need a transformation. In this case, the recommended transformation is none. You do not need a transformation. If you did, you would go back to the configure button and choose the transformation that it suggests, and then reanalyze the results, reanalyze everything. And then finally, you have to interpret using the model graphs. Okay, I'm not going to get into that right now, but the response surface analysis procedure is almost the same. The ANOVA, the diagnostics, the graphs are all the same. What's different is that we start with a fit summary button. This has statistics that will compare some different polynomials, and it will suggest a model. So let's look at that with a different file. Okay, so this is again a 5-factor design, but this is a central composite design. So more responses, more data. I just wanted to show you the analysis of this one, starting with the fit summary, which looks at a linear, a 2-factor interaction, and a quadratic model. And you can see that the quadratic model is suggested. The quadratic terms are significant. There is a little bit of lack of fit here, just a tiny bit. The adjusted R squared is great. The predicted R squared is lousy. It's really bad, but it's the best option that we have. So the software has a little algorithm it goes through and says that the quadratic model is the best starting point. So we're going to go ahead and use that. By default, it will take whatever is suggested and it will put it right up here in the starting point. So we can go ahead with the ANOVA and look at the ANOVA. And again, our model is significant and we have significant terms, but we also have a lot of terms in here that are not significant. Now, this is one of the errors that people make. They just go ahead with the full quadratic model. When they're doing this, all of these insignificant terms are noise. They are just noise. They do not belong in the model. And if you look over at your R squareds, the adjusted R squared and your predicted R squared is really low because there is so much noise included in your model. You're actually filling your model with noise. It's not good. So you need to do model reduction. And so we can go back up one step, and you can either take out terms by hand by just double clicking them. If they don't have an M by them, then they're in the error, the residual. Or the easier way to do it is to simply use the auto select method, automatic model selection. And the criteria of AICC with the selection method of backward is my favorite criteria. That's the only one I'm going to show you. Again, there is a webinar that goes through the ins and outs of these, but if you use this default AICC backward, it goes through and it excludes terms one at a time and recalculates things. So you can just click accept, and it will remove a bunch of terms, and then go on to the ANOVA, say yes to hierarchy. And you can see that we have reduced the model greatly. There is still a term in there that's not significant, but that one's okay because that is supporting that AC interaction. So that one's acceptable. That improves our lack of fit, and it also greatly improves the predicted R squared. So the two things that I want you to think about are watching the box Cox to see if you need a transformation, which we don't here, but also doing model reduction. Those are very, very key to the analysis. And there is, if you look for the webinar, keys to analyzing a response surface design, that will go through this again in more detail. So whether you have a factorial or a response surface design, don't overfit the model. Don't include unnecessary terms. Only include terms that are statistically significant or needed to meet model hierarchy. All other terms belong in the residual. For response surface and mixture designs, use the automatic model reduction tools, and just use the AICC and backward method. That is a tried and true method. The adjusted and predicted R squared should be in reasonable agreement with each other, within approximately 0.2. If they're far apart, that's a sign that the model has too many terms in it, that it has been overfit. And check box Cox for a transformation recommendation. Okay, let's talk about confirming the results and really the steps that you have to do to wrap this up. So after you get the basic analysis done, well, then you have to interpret the model graphs. And subject matter knowledge really comes into play here. There are many graphs, from interaction graphs to contour plots to 3D surface plots. They are all telling the same story. They are all just ways of modeling your prediction equation. Now, backing up, if your prediction equation is not modeling well, then those graphs are drawing a picture of something that's not modeling well. So once in a while I get the question, well, can I didn't get a significant model, can I still use the graphs in my report? Well, absolutely not. You know, the graphs are a picture of your model. If you don't have a good model, then you don't have good graphs, even if they're pretty and in color. Okay. You can use numerical or graphical optimization to find your sweet spot. And there is a YouTube webinar on that, really details on how to use optimization. And then you have to confirm and verify the results. Ask yourself, do the predictions work? And then finally write a report. So I'm going to look at these last two things. Confirming the results. Different ways you can do this. Well, number one, you can find your best set of conditions and do one single run at those optimal settings. But does one run provide a good estimate of the process and the natural process variation? Probably not. So this is not something I would advise, just doing one run. You want to gather several observations at the optimal settings and then use the confirmation node. If the mean is within the adjusted prediction interval, then that model has been confirmed. So let me just demo this. I'm actually going to go back to that previous file because it's a little simpler. And I'm going to use numerical optimization. I'm going to maximize yield. And I'm always going to change these settings. I want to say, you know, the minimum acceptable yield is 80%, and I want to drive it up to 100, you know, if possible. And so what solutions will get me that? And so there's a couple different views here. The ramps view shows that if we set catalyst high, temperature high, use nitrogen, you know, it'll give me good results. So I'm going to take that into the post-analysis section where it says confirmation. And it puts those results into my factors tool because it's solution number 1. So it uses those results. And then I can tell the software that maybe I want to do 4 runs at that condition. And so I have to go out back to the process and do 4 runs at those conditions. And then I can type in my response information. And I've got to bump my data up a little bit. If the average, so down here, gives you a data mean, the average of those 4 runs, if the average falls within your 95% prediction interval, then you can say that the DOE analysis results have been confirmed. If the results did not fall within that interval, so now I just edited so that I didn't have good results, and it turns it red. Whoops. Yep, makes that red. And I am outside of that. And then I would have to go back and ask myself, did I analyze well? Is there something else going on? You know, you just have to ask scientific questions. It is probably not an analysis problem. It's probably something like the process shifted a little bit over time, or you know, something from a science standpoint. One other thing you could do is to go to your optimum and run another small experiment around those settings. Treat the optimal setting like a center point. Pick a small range for every factor, and then compare the predictions at the center point in the new experiment to the prediction interval calculated by the previous analysis. This would help you get an idea of the sensitivity of that optimum setting. You know, how can you vary the factor settings a little bit around that point? So there's some extra benefits. I think most people will do number 2, you know, just do some extra observations. And if you did that, that would make me happy. Lastly, you have to tell the story. What do you include in your report? And that is answering the question, what does the audience need? So it depends on your audience. If your audience is corporate management, then you might do a quick summary of the DOE objectives, you know, and just some basic outline of what you did, and then the final results and your conclusion with evidence of long-term gains. So did you reduce cost? Did you improve quality? You know, the management is going to judge the success of your experiment on what you can do for the business. So that's, you know, definitely you need to go back and do those confirmation runs and, you know, make sure that you're going to have lasting results. Now, if you're doing a journal research article, then it's a little bit more complex. You certainly want to include the objectives of your experiment and basic design information. You know, did you use a 2-level factorial? Did you use a response surface design? What type? Those types of things. Then you should include your ANOVA. You should include summary statistics like the adjusted and predicted R-squared. Include your prediction equation. And then relevant model graphs that tell the story. Be careful in selecting those graphs. Make sure they're the ones that tell the story the best. But again, don't just, I have seen articles, I review some journal articles where they did put their basic objective and said what type of design they used, but then they jumped right to a model graph without any supporting details. There was no ANOVA, there was no prediction equation. They just used the graph to tell the story, and that wasn't acceptable. You have to give the information to support those graphs. You need to include the data. And if it's a lot of data, then put it in an appendix. But if it's a, you know, somewhere 16 runs or so, you should be able to include that right in the report. And you need to include information about how those final results were confirmed. You have to basically include enough information so that your results can be verified by others. You know, if your results are not verifiable, then it's not a believable and really acceptable research article. So think about including all this information. I know it's a lot, but you know, that's what you need to do. All right, so we've spent nearly an hour going over, you know, these 4 parts of planning the experiment, starting with planning your DOE based on what type of objective you're doing, some keys to running the experiment, analyzing the data, and confirming the results. As a reminder, these slides, if you want to go back and look at these slides and the recording, are both going to be posted on our website. You go to Learn DOE, and then you can select webinars or go to this path directly. As additional resources, we have these textbooks available. They're available via Amazon or the publisher, Taylor and Francis, and they're available in soft cover or they're ebooks, and they can be purchased or rented. So even all of you who are viewing this from international locations, you can purchase ebooks, you can rent these for a very short time and read through them in a couple of days and get a lot of really key guides from these books. If you want to dig deeper and get more comprehensive education, then we offer public workshops on factorial and response surface designs and a workshop on mixture designs. And those are available both publicly and privately. We can customize them for whatever type of situation you guys have. Okay, so I am going to look at the questions in the box and see if there's anything I can answer on here. I would like to thank you for attending today and hope you've gotten a lot out of this.